calcium geothermal. What's that, Charlie? What in calcium? But I'm going to speak in English today. I've been studying Mandarin for 3 years and nobody understands me. Anyway, we've been working here in Taiwan for 5 years now. And we've been assessing, I don't know how you express it, but raw, open field, potential geothermal sites. In other words, no intervention. There's been no wells, there's been no EM, there's been nothing. So what are we using to get an assessment of potential for geothermal development? So this is me, of course, and then my partners are in the U.S. We have a partnership with them. You'll hear about their instrumentation. We have a partnership with Professor Li Xiaoxing here, and his team, all here, and then our new student here, G. Starting a PhD on this topic, so we're very pleased, and we're making inroads into influencing geothermal development in Taiwan. I'm going to talk about tomography and rock physics. First, I'll talk about tomography. Tomography is our basic source of information of what we want to understand the subsurface. If you think about it, very few technologies are telling you what's going on beneath the surface. You have geology, springs, you have geochemistry, but very few technologies are telling you what's going on beneath the surface. You have EM, and you'll see some differences with that. So we feel we have a technology that we've been working on developing for years that can give us valuable information from the beginning to the end, because it also can monitor reservoirs. But so what is tomography? Well, we have instruments at the surface of an area of interest. Usually this is something like 5 by 5, it could be 10 by 10, but you have to add more instruments, because to get high resolution, we want an instrument recording about every kilometer or less. What are we recording? Little earthquakes that are occurring at depth. So this is the energy comes up through your volume. It gets modified by the conditions of the volume, the water, the permeability, the fracture zones, the consistency of the rock. So all this energy that leaves a little earthquake comes up and recorded at the instruments. Of course, you don't do it from one earthquake. We need typically 300 at least little earthquakes, by the way. And they occur quite frequently. In Taiwan, we can get a lot of earthquakes in a very short amount of time. Even in the U.S., I'm not sure anybody here from Nevada, but over California, we have plenty of earthquakes in California, but in Nevada, surprisingly enough, we have very few small earthquakes. But they occur there too. So just to get you started here, this is typical tomography result of a resource in detail. And this is the same resource assessed with EM. So EM it does identify the same conditions, but much less resolution. But not only do we get more resolution, as you're going to see, we get a lot more information. This might tell you about fluids, but we'll tell you about the fractures, about the permeability, about the chemistry. So here is a typical void with earthquakes occurring in it. Something like this is 10 kilometers, in this case, 5 by 10. So we developed an end-to-end solution for rapid, inexpensive exploration, modeling, monitoring, and providing drilling targets for reservoirs and active seismic areas. I was going to say, in Nevada, they say, well, there's no earthquakes in Nevada. Well, when you put in our instruments in, you find out there are earthquakes there. But let's talk about rock physics. When you record these earthquakes, you do the tomography, you get an image of what's going on in the depth. How do you interpret that? Well, we interpret that with rock physics. It turns out with recording the VP and the VS, which is the P wave and S wave travel times, and the QP and QS, which is the attenuation properties, those 4 pieces of information can be manipulated with mathematics to provide several elastic parameters of rocks. These are typical elastic parameters that are mathematically, physically derived of what rock behavior can be. For example, Poisson's ratio, bulk modulus, shear modulus, lambda. You'll see all these in your physics classes when you derive the wave propagation in a medium. You'll see all these parameters. And so we derive these parameters, and each one of them tells you something else, something different about the geology. It'll tell you, for example, high shear modulus, very often that's due to the case of a very weak zone. But shear modulus doesn't see water, so it will tell you about the geology excluding the water. Whereas bulk modulus will tell you something about the water. So you can have a highly fractured, highly permeable zone and have a very low shear modulus, but a very high bulk modulus because it's full of water. This would not see the water, it would only see the geology. So every one of these tells you something different about your geology that you're looking at. Okay, so where are we going from there? Oh, here's the kind of things we try to get out of our information. We get cracks, fractures, and faults just from the locations of these earthquakes. I'll talk about that later. We get moment tensors, which is identifying how the earthquakes rupture. So you might find a zone where you can see ruptures of a certain type. For example, normal faulting is more common to propagate fluids from depth to the surface. Steam, we can identify steam by Poisson's ratio. One of our elastic parameters can identify what is steam and what is water. You'll see an example of that later. Like I said, for bulk modulus, you can identify fluids by Poisson's ratio as well. And if you look at all of these, plus your other pieces of information you might get from other sources, we can identify the porosity, the permeability, and the saturation of the volume. So these are all things you get of your volume that you may not see at the surface. Keep track of my time, I got 5 more minutes. I just want to point out that the surface very often is not what's really going on. And where we are in California, our geothermal wells, you'll see some examples of that, are 25 kilometers from the surface hot springs. We see hot springs everywhere, and they make hot spring spas, and nothing where we have the actual geothermal resource, because Mother Nature does not always obey properly. You don't go to a hot spring at the surface and drill straight down and find a geothermal resource. Often, in fact, in Taiwan, we find these surface wells, 1,000 meters or less, are tapping into rainwater, leaking into the surface, and getting hot springs 40, 50, 80, 90 C, but the actual real geothermal sources are down 2 and 3 kilometers, not even connected. So if you're going to take a hot spring and start drilling straight down into that hot spring, you may be happy for 10, 20 kilowatts, but you're not going to get 40, 50 megawatts out of that. Okay, am I going to run out of time? I've got to keep moving here. So this is what we're doing with rock physics. We're trying to, a lot of these rock physics parameters are developed in the oil industry. There's very little of this was done in geothermal. But we got the idea that, well, all this research in the oil industry, we could apply some of that to geothermal. They've been doing this for decades. Rock physics is a primary degree of study for anybody going to work in the oil industry. But and what they found are things like this. If you look at Poisson's ratio down here, if you look down here, different values of Poisson's ratio will tell you different things about the water. And this is, we really got this from oil and gas, but we're trying to apply it to geothermal. For example, very low Poisson's ratio can indicate steam. Very high can indicate water. Mostly in the middle is normal material. No water, no steam, just sort of your normal geology. In field instrumentation, we built our own instruments. We found them to be very inexpensive. We can develop a lot of these in a very inexpensive manner. And they have all these kind of attributes, which really, my partner, I told you at the beginning, is the genius in electronics. He's really better than what's commercially available, but we keep this for our own use. So they're very valuable, and they record the little small earthquakes. We have students here in Taiwan work with. You can guess which ones are from the U.S., these two here, but the Taiwan students, and the instrumentation is easy to install, quick, and they record these very, very sensitive, very small earthquakes. Like I said, in Nevada, they were saying there's no earthquakes. How can you do what you're doing in Nevada? Well, you put these out there, and they are earthquakes. They just didn't feel them. They just didn't have small, sensitive instruments to record them. not doing it for time. I talk too much, I know. And we like I said, we give a shout out to Jerry here. He's here. Just got married a week ago. Congratulations, Jerry. And we build them ourselves here in the lab at Professor Lee's lab. So we just crank them out because we have 200 or 300 of these. And that's a massive amount of data processing, which we've also automated and which we can process pretty quickly now. But it's all a step. So let's look at Taiwan. We've been here in Taiwan now for 5 years looking at some of these different geothermal resources. But I'm going to talk about this up here. Very interesting area up here, which is a volcanic area. Most of this is accretionary prism, and here is mostly volcanic, but it's also hot up there because of the volcanoes. So here's one of our results, in the tomography result, for a volume that's about 5 by 5 kilometers in area, and then 5 kilometers, so it's a big cube of the Earth of interest. And this is what you might call normal values here. This is Poisson's ratio. Normal will have two big cavities, A and B. But the rest of it is kind of like normal geology. So, okay, fine. So what happens with A and B? Well, it turns out B fills up with steam. It's a very low Poisson's ratio. And A fills up with water. So we have a water reservoir and a steam reservoir right next. It turns out they're right along a fault here, which is the source. But here it gets us closer to the volcanic heat, and it's turning it into steam. Down here is water, but either one is a good reservoir because they're both hot. Depends on what you want to do. Here, if you isolate them, here's your two reservoirs. There's some wells that have been drilled in there to validate what we've seen. And so you have the steam reservoir as B, and the water reservoir as A. Here's the detail of your reservoir. So here we can provide you with a drilling target. If you were going to drill here, make some plans of what you were going to do. All right, now I'm going to go back to California, the geysers. Just to point out that this is San Francisco. Berkeley is over here. Up here is the geysers. It's an hour-and-a-half drive. It's our outdoor living lab. We go there all the time to do experiments, to get information that we can test. Here's a test we did here with a dense network of recording stations over 5 by 5 kilometer area. And we're looking at these wells here. There's 4 wells. So this is a case where we already know what's there. This is where we validate and test our theories. We already, in cases where we know what's there. So here is wells here drilled into this. This is Greywacky. It's 260 degrees up here. It's 400 C down here. 260 up here. And then it cools up in here. But this is all Greywacky. Volcanic heat source down in here. It gets really hot, really hot. So what do we do with this? Well, we look at water injected in these wells. So there's water being injected in these wells. And what we found is that it creates little earthquakes. When you put cold water into 200 or 400 C temperature geology, you get a lot of little earthquakes. And here they are coming out of the well. And here's what the water does. The water has altered this volume, which is mostly normal geology up here with steam. A lot of it's steam. It's very hot. But here is where water has saturated it. So we can see when you inject it, we can see what water has done to this. The point is here, we did our tomography. We located the earthquakes. We identified an anomaly, and it fits exactly below the well where water was injected. So we gave you confidence that we see what we see is real. We know that they put water in. We know that at the bottom of the well, we see the effects of it would be theoretically what water would do, and we see it. Over here, we see nothing because they didn't do anything. They haven't started injecting water here yet. This is a dry well, pristine well, drilled into very hot material, so nothing happened. And here's the 2 other cases. But here, they started injecting in here right away. We saw the earthquakes, and we see the water at the bottom of the well, more validation of what we're doing. But I want to point out, this was a failed experiment because they drilled 2 wells, actually. The well over here, and the idea was to put water down this well. It would induce fracturing and get a flow of the water to the second well, and then we get an engineered geothermal system. Big mistake. You don't drill the second well until you know where the water is going or where the fractures went. And so here, for example, you might have done better to drill the second well over here instead of over here. But they've learned now, and Forge, our second developed area, they're now putting the well in later, not at the beginning, hoping to reach it with fracking. But if you do hydrofracking, you can see where your fractures went. When you start injecting water, you can see where your water went. Then you can drill your second well with an enhanced geothermal system. I know I'm running out of time, so I'm done with that. I'm going to go on to, I'm just going to skip that. I know I'm running out of time. Go to Taiwan, and now we're going to go to the Philippines, okay? In the Philippines, they already have a geothermal system, well developed. So here's well, we did the tomography because there they want to do reservoir management, not reservoir exploration. So here's the volume of their area. Here's the cap rock we identified. Here's their wells. Here's the heat source below it, and here's the reservoir in here. So there's some questions to be asked. Like in our case was, can we expand the reservoir as it is, which is over here, to north of this fault here? There's a fault here. The question was, can we expand the field over to here? We said no, because over here, look at this. This is QS, and she's written a paper about this. It's very indicative of water, like they have in their reservoir, very good resource of water in a hot reservoir. Over here is a fault, and over here is QS is very high. It flips exactly over that fault. It flips from very low to very high. Well, very high is dry. Very low is wet. Oh, I got 5 more minutes. I thought we only had 20 minutes. Okay, good. It flipped over along this fault. Our tomography, in other words, is so detailed, so such good resolution that across the fault we can see a flip over from a very saturated area to a very dry area. Well, unfortunately, they didn't believe us at first, and they drilled anyway because they had other surface indications that they believed and found a dry well. We said sorry, but then they've learned, and now are not expanding in that direction. That's the end of my talk. So I just say we've improved data collection and processing for reservoir monitoring. You can start with an area where you know nothing, and we talked to John O'Sullivan here about coordinating with his approach. We're putting some ground truth in what you know at depth with what he's modeled for all the different possibilities of reservoir models, and I think the two could go together well. Well, this is all the improvements in instrumentation and computer processing where we reduce the time. And so all this is reducing time to get the results. Because of that, we can get near real-time reservoir modeling. If you remember that well where they had not seen any effects of water, when they started the injection, they immediately saw the effects of water. Well, if you're monitoring a reservoir or you're monitoring hydrofracking, you can see almost immediately where the water is going. You have a good vision of what's going on at depth. So for reservoir management, for identifying drilling targets, for assisting in hydrofracking engineered wells, you can monitor what you're doing and see it. And so the other point is that the micro-earthquakes, the little earthquakes we record, can be used along with rock physics to apply some very detailed and important information for geothermal systems.